So we have our first keynote speaker, Professor Faisal Hossain from the University of Washington in Seattle. Dr. Faisal is leading the SASB research group, or Satellite, Sustainability, Water, and Environment. And the overarching research of Dr. Faisal is to making access to water information a fundamental right for all the humans. And to do that, Dr. Faisal is using remote sensing to attain the sustainable management of water resources in transboundary basins. I want to say also that Dr. Faisal has been recognized by many organizations here, like NASA, the American Society of Civil Engineers, the American Geophysical Union, just to name a few. And Dr. Faisal is currently serving as the applications lead for science team of surface water ocean topography, or the SWAT mission. And something unique about Dr. Faisal, he's very interested in filmmaking to serve our scientific communities, just not just any kind of film, but this kind of scientific films. And Dr. Faisal in 2017, he launched the first student film contest here in the US for the engineering majors. And so, I mean, I encourage everyone to visit Dr. Faisal YouTube channel. You'll see many videos on his research, and it's actually very interesting. So Dr. Faisal will share his experience on satellite remote sensing and giving us like perspectives on the past, present, and future of satellite remote sensing water resource applications. So please join me in welcoming Dr. Faisal Hossain from the University of Washington.
All right. Well, thank you, Dr. Hisham, for your nice introduction. Very kind. So as Hisham mentioned, I am Faisal Hossain. I'm at the University of Washington in the Department of Civil Environmental Engineering. And really, this is, I think, a very wonderful workshop that Hisham is organizing. And let's hope it's useful for all of us. So good evening, I guess, to all our friends, brothers and sisters in Egypt. Good morning to those in the USA, and good day to wherever you are for the rest of us. I'm looking forward to making this kind of an overview presentation with all of you that will hopefully set the stage for this workshop. It's like a big picture of what satellite remote sensing can do, but what are the pros and cons of it when it comes to managing our water resources. As you know, this workshop is titled Sensing Rivers, so it is really a fundamental part of water management. Also, I want to tell for those of you who are in Egypt, I was in Egypt last December and I really had a wonderful time, and I immediately fell in love with the Nile River and the entire water system out there. And I hope I'll be able to visit again after this COVID-19 is behind us, maybe with Hisham one day. So let's get started. Hisham already mentioned the etiquettes. If you have any burning questions, you can always, of course, use the chat box anytime, but you can I don't mind if you want to unmute yourself and ask a question right away. Otherwise, hold on to your questions till the very end. So basically, when it comes to managing our water, I think the most fundamental question we ask ourselves is, how much do we have? Where do we have? When will we have it? Or how much did we have yesterday, last month, last year, or ahead of us, a week ahead, all that. And to answer that question, of course, we have to be able to monitor the water resources. So I'm showing you some pictures here that are based on my own experience growing up. So on the left, you will see there's this bridge. It's called the Hardin Bridge. It's on the Ganges River. I grew up on the banks of the Ganges River. Just 1 month apart, you will see that the river becomes full with water, but if you are there a month early, it's completely dry, mainly because of a barrage upstream in another country that diverts the water. Then in 2010, when I was living in Nashville, USA in Tennessee, there was this big flood. You might have heard about it. It pretty much inundated the city of Nashville. It was due to a very extreme rain event. And the dam also upstream of this river called the Cumberland River started releasing a lot of water. And of course here, this is a urban flooding environment situation where you see that just with a 30-minute thunderstorm, this whole place gets inundated. This is in the city of Dhaka in Bangladesh, you see. And then you have droughts. You either have too little or too much water. So let's kind of step back and ask ourselves what's going on. What are the bigger global drivers? So our population's increasing. And with that, what we see, there's this march of urbanization. The cities are getting bigger. They're becoming large cities. Large cities are becoming mega cities. As you can see here in Cairo, it's a mega city. We have a couple in the other parts of the world. They all tend to be in the river deltas or in, next to a river, most of them. And these large, concentrated, organized way of living represent a big resource hub for resources like fresh water, energy, health, food ecosystem. But since we're all focused on water, you know, there's a dependency on all these other resources like energy, growing food, health, maintaining ecosystem services. And to ensure we have a steady supply of water, and I'm sure, you know, those of you who are in North Alexandria or Egypt would understand this better, or better than most of us, is we try to make sure we have reliable supply, so we build systems. In this case, we build like batteries, we call them dams. So whenever the natural water supply is less than the demand, you draw from your stored water. Whenever, of course, you have enough, you don't. So in this figure that you see at the bottom left, you know, since the 1900s, we've been steadily building lots and lots of dams. The y-axis shows how much you're storing behind the dams in terms of cubic kilometer. Now I think it's 15 or 16,000 cubic kilometer, which is about 2 to 3 centimeter depth of all the ocean's water, if you kind of want to think about it. And these are necessary to sustain our civilization of the need for energy, you know, food, health, and ecosystem needs. So finally, to wrap it all up, if you just focus on dams as the water systems that we're building, I think all of you probably appreciate or understand that most of them today are being built in the developing countries. You know, the industrialized world or the developed countries are really not building these water systems anymore because of they've either built wherever they could, or they just, you know, because of environmental conditions, or they have other options or solutions. But rest of the world, whether it's Southeast Asia or South America, you know, Africa, we're building lots and lots of these large water systems or batteries, or we call them dams. Okay. So it's a little stuck. There you go. So when it comes to managing our water resources, I like to talk about 4 key issues that we have to address if we really want to solve the challenges of monitoring. One is, of course, transboundary issues. And it's not just sharing the water, it's actually sharing also the information, as Hisham mentioned a little earlier, in the right time at the right place. Then number 2 is, you know, measuring, monitoring using the conventional way, putting a gauge on the river or a bucket to measure rain, or, you know, putting a radar system on the ground, something like that. And the third is, of course, the economics of this. There is a cost to maintaining these networks on the ground, and cost to train staff, agencies. And finally, there's this human resources aspect. You know, these measurement networks and technologies, they keep evolving, they keep advancing. So how do you keep up with it? The science keeps progressing. So how do we make sure that the staff or the agency mandated with the management of water resources, the monitoring of water resources, actually are fairly up to date? So in my short talk today, my overview talk, we're not going to go deep into all this. I'll try to present the value of satellite remote sensing for all these 4 key management challenges that we face. Just touch down briefly on each one of them. So of course, we have limitations with ground networks. Here are some pictures you see. There's a gauge. It's a typical USGS gauge or a river gauge. You're measuring the river level. Here on the lower right, you see a rain gauge, solar powered. It's measuring rainfall. Here there's a little automated weather station that's being set up. Actually, this is in the highlands of Ethiopia by one of my students about a decade ago. Here in the River Brahmaputra, they're doing discharge measurement, doing ADCP acoustic Doppler contour profiler concept. And all of these, of course, they have challenges in terms of cost, manpower issues, and also the coverage. You know, they're typically measuring the value of, say, what you're interested in at that point. So the river level you get here at the bottom is at that point, not everywhere. The rainfall that you're measuring is only at that point or in that little area that you have. You're not getting it over the entire area. And the other aspect that's happening we see globally is our ground networks that we have for measuring rainfall or stream flow or soil moisture, they're not really expanding. They're actually declining, or we don't have enough coverage spatially. So here you see on the upper right, these are basically the rain gauges we have around the world and that are functioning. They share the data with the WMO, World Meteorological Organization, to create a data product called GPCC, Global Precipitation Climatology. I can't remember what the other C stands for, but you see some gaps here, you know, like in developing countries, like in, say, Africa, especially in the tropical region where you have a lot of rain, South America, there are not enough gauges. In fact, if you collected all the rain gauges into one place, they take the size of a few tennis courts, which is very, you know, infinitesimal compared to the Earth's surface. And besides, what do you do for the oceans? You know, you can't really put a lot of gauges on buoys to measure the rainfall over water. Here you see on the left side, these are the stream flow gauges. Basically what it's showing you is the number of gauges we had as a function of time that were being shared the information for. So the y-axis is your timeline. And we were doing pretty well. We peaked at around 1980s and 90s, but ever since, you know, 2010, you see it's going down. The x-axis is the number of gauges you have. Left side is monthly gauges, right side is daily gauges. So these are what are shared with the GRDC, Global Runoff Data Center. So these are the reporting gauges where you have the data available fairly quickly to do some, say, holistic basin scale analysis by any country or any entity that's interested in that. And finally, at the bottom, you see basically is a color is used for streamflow gauges, where wherever you see blue, it means it's fairly up to date, it's reporting data. Wherever you see yellow or red, it means that data that's being reported to the GRDC center, last time I did it was in the 70s or the 80s. So they're almost like, they're not functioning really anymore. And then the other aspect, you know, so you have this infrastructural challenge. There is this transboundary challenge in the sense that if you look at the map of nations, this is what you see. These are the boundaries of countries. Now, if you compare it with the map of river basins, you see very different boundaries. So what this really means is that we have a lot of rivers that are international rivers. And of course, you know that because Nile is an international river, or call it a transboundary river. If I show you a summary, here is, like, globally speaking, the number of countries that are part of an international river and the percentage of that basin area it occupies. So you see there's about 39 or 40 countries that occupy most of the river basin area. But there is a lot here in the midstream or downstream, right? 14, 11, or 17, 10. They do not occupy the entire river basin area. What that means is that a lot of these countries, they either get a lot of stream flow from upstream or they contribute a lot of stream flow to the downstream country. And a good example is the Mekong, which is one of my favorite rivers because we study a lot. You can say the same thing about the Nile River. I think it goes to 11 countries. Globally, these are the maps of international rivers. So you have this challenge of, you know, these river basins being international. It's not enough to just have a good ground monitoring network. You have to have a situation where you are sharing data at the right time. So you have to work across national agencies. It's difficult enough doing it within an agency. How do you do it, between or among agencies of different countries? That's a huge challenge, even if there was a good network. And then, of course, you have the cost and manpower issues. So then this brings us to this case is that, can satellites up in space that do remote sensing, can that be the answer? Can it be the answer to address your transboundary challenges? Can it be the answer to address your infrastructure challenges, your economic challenges, and the human resources? I'll come to it later. I'll talk about it. So since 2010, we've been living in an era of very exciting prospects for water management using satellite remote sensing, because since 2010, we've launched many satellite missions dedicated exclusively for water management or water resources monitoring. So on the left, you see GPM. It stands for Global Precipitation Measurement. This was launched in 2014. It was a multinational mission. Multinational means NASA, the Japanese Space Agency, Europeans. They all shared their resources to create a global system where you can have rainfall information at the scale of, I think, every 30 minutes and 10 by 10 kilometer, almost like 70, 80% of the Earth's surface. So it's a very phenomenal system now, and it's available to anyone if you have internet access. Here's a SMAP, soil moisture active and passive. So this is dedicated exclusively for monitoring the wetness or how dry the soil is. And that data is also available. It's a global mission. There's another one that's coming up called SWOT. And many of us, like myself, were a part of the applications effort. SWOT stands for Surface Water Ocean Topography. This will be launched in 2022, hopefully. It's a French-US mission with Canada and UK also contributing to it. And its goal is exclusively to monitor surface water. So the water, the discharge in the rivers, the storage in the lakes, the storage behind dams. And that's its goal is. Of course, it will do some oceanography issues, but here we're talking about sensing rivers, so I'll just keep it confined to hydrology here. And then on top of all this, we have also lots of Earth observing satellite missions, meaning looking down on Earth and taking a pulse of the Earth's surface of the atmosphere, temperature, wind speed, humidity, so radiation, or you can talk about vegetation, land cover. All of this helps us get a better understanding of what's going on to the Earth's surface that we need to monitor and manage our water resources, maybe to set up a model, maybe to create a better decision-making system. And I'll show some examples in a short while. And as Hisham mentioned, in the very beginning, we have about, I think, 2,000 or so satellite systems out there looking down. So we're living in an era of big data with lots of data on Earth related to water becoming freely available more and more as every day passes. Now, what is remote sensing? This workshop is not a crash course on remote sensing itself, but I think it's worthwhile to, just kind of touch down on the basic fundamental definition of remote sensing. So here, remote sensing basically is, in case if you didn't know, is trying to infer information about your target, which may be very far away, without really being in direct contact. So you're typically using some type of energy, and based on the energy interaction with your target, you are then inferring what the target is. Your target could be rainfall, your target could be discharge, it could be soil moisture and all that. Of course, although our typical energy is electromagnetic, sometimes we can use other forms of energy like sound, sonar. Here's a little quiz for you, which one is remote sensing? I'm sure you agree that having an ice cream is not remote sensing, right? This, on the other hand, will be remote sensing because it fits the definition. And just to talk a little bit more about remote sensing. So I apologize, sometimes the transition takes a little bit of time. Okay. So there are basic steps to it. I won't go into the detail, but typically you can have like 7 steps Let's just focus on the schematic of it. So you have a satellite up in space. It's looking down on Earth. Your target will be on the ground surface where C is. You may or may not need the sun. If you need the sun, then the goal of the sun is to illuminate your target and get the reflection from the target that the satellite will measure. But sometimes a lot of satellites do not need the sun because they measure the target's natural radiation. So like they can work all weather. Or sometimes the satellite may have its own energy source and it may shoot down a beam and then see the response from the target and what came back. So with the sun or with the satellite's own energy source, it will figure out based on the interaction with the target, the energy, what that target could be like. And then of course, then it relays the information to a ground station. This is a GPS satellite that has to track the location, because if you don't know where the satellite is when it took the measurement, it's really useless because you need to pinpoint that value to and longitude, latitude, and time, right? And then once you figure that out, you send it to a data center. Data center then creates data products and with some guidelines and then makes it available for use or consumption. In this workshop, of course, you will start from somewhere here where you'll be accessing data, or you'll be shown some examples of how to use the data that's out there from these satellite missions to understand the state of our water resources. And finally, about remote sensing, one thing that when I teach a course is I always like to stress the golden rule of remote sensing. What is the fundamental principle where it works? So the golden rule really is the target, whatever that you're interested in remote sensing. Again, like I said, it could be vegetation, it could be rainfall, it could be soil moisture, it could be discharge, it could be storage in a lake, say Lake Nasser, how much water Lake Nasser has. Whatever it is, that target has to stand out from the surrounding areas, the background, in terms of the way it interacts with the energy that the satellite sensing is dealing with. So if it doesn't stand out, then it'll be camouflaged, like you can see here, you know, in this picture. If this person is your target, but if the background is the same as the person in the wavelength where you see, you won't be able to really decipher what that person is, as you can see here. But if you have the person stand out because of maybe a different color, then you could then do a good remote sensing. So I'll show you an example and then I'll end with the remote sensing part here. So here, for example, you know, there's a wavelength called near infrared, which you get naturally from the sun. And near infrared actually is good for detecting water or vegetation because when there is water, it absorbs, it gets totally absorbed. When there's vegetation, it reflects a lot. So imagine you have a tree and then you have this near infrared ray from the sun. You have red, you have green, you have blue. Your infrared, of course, bounces off. Your green bounces off, everything gets absorbed. But then if next to the tree, if you had water, then your near infrared would get all absorbed and the rest of the colors, especially blue, would get reflected a lot. Other colors will get reflected a little less. And using that wavelength, then wherever you see a lot of absorption or dark colors where there is no near infrared, you know there is water. Where you get a lot of reflection, you know there has to be vegetation there. So this is how we typically oftentimes detect vegetation, especially in environments where there might be some wetlands or lakes and all that. Okay, so let's go to the next. What can satellite remote sensing do now? You know, we've talked about the challenges and we talked about the potential and the prospects. Let's talk about just very briefly where we are today, and especially what we've been able to do in our group, so that hopefully you might get a little excited after learning about all this in the workshop and want to use it moving forward. So I'm just presenting from our group's work. So this is from Nishan Biswas works, who will be presenting right after my talk. What you see in front of you is dams. The red ones show the dams that will be built, and blue ones were already constructed in operation. And like I mentioned, you know, if you focus on the pink areas of the land, these are the developing countries typically, or they are less industrialized, you have challenges to monitor the water the conventional way. So remote sensing would be most useful if you can apply it. And we want to know what these existing dams that we are building or will be building are doing to the state of the rivers. In this case, you see a map in front of you where the more the color red is, means it's more regulated. So it's a metric for CSI, it's connectivity status index. So 100% means it's free flowing, it will be blue. Red means it's really not free flowing anymore, it's artificial flow, it's controlled by man. And we want to know how dams are impacting the free flowing nature of rivers downstream, because that helps in water management. So what can we do? Well, there's actually a lot you can do. Dams are basically nothing but traffic light systems. You may recall, of course, you have traffic lights, but in the olden days, you have to have a traffic police who would regulate traffic. So, you know, you stop the water coming your way, you store it, then when it's ready, you let it go, right? It's just like that. So if you look at a reservoir system or a dam, I'll use them interchangeably. There's water flowing in, there's water leaving, there's evaporation, there's precipitation, and of course there's storage here. And then you can have some seepage or losses, we'll ignore that. But these are the key mass balance components. Your outflow has to be equal to what is flowing in minus what's leaving the system. We've ignored precipitation here, but you can add it in. It's part of the inflow actually. And then your storage change. So these are the key components. And turns out you can actually use satellite remote sensing on its own or with the help of a model to estimate all these components. And you can piece them together almost in near real time or in operational fashion to see how each one of these hundreds and thousands of dams are behaving and operating almost in near real time. And what I mean by near real time here is not every, you know, with a latency of say a day or a week, but let's say every month, which for reservoir management is quite acceptable. So you can see what happened last month or the month before. So basically we use a lot of cloud computing, and Nishan will introduce you to that. That way you don't have to download all those terabytes and terabytes of data. And you have to figure out the reservoir's bathymetry. So there is a freely available data set called SRTM, Shuttle Radar Topography Mission. And using that, for all of these reservoirs out there, we can get a fairly decent idea of the relationship for those reservoirs that tell you for every elevation of water surface, what is the surface area of the reservoir? Because once you know that, because you may have learned that in your standard water management class, you can then figure out your storage change for every elevation change or surface area change. Or you could do reservoir routing or some kind of flood routing to the reservoir. So you can do this without any ground-based monitoring or data or surveying data, which you won't have anyway for those thousands of dams in developing countries. And then you can use these other satellites. So these are names of satellite missions that use the optical, the visible wavelength to see the land cover, especially to see where the water is. So it can estimate surface area of reservoirs. So you can get it from all these satellites. Then, like I said, if you know the difference in surface area 2 different times, you can actually get storage change like that. Then you can set up your model. You know, you need to know the land cover, how it's changing, where you have trees, where you have bare soil, grass. And from a lot of satellites, you can get rainfall information, humidity, wind speed, and you can put that all in your hydrologic modeling. In this case, we use VIC modeling a lot. It stands for Variable Infiltration Capacity. And you can have a modeling system running that on the other end, it's spitting out or outputting to you stream flow, evaporation for every grid cell, maybe your soil moisture, or maybe some kind of base flow that you need to know. So these are model information. That way you can get, in this case, reservoir inflow, which is what we're interested in. And finally, you put them all together, you piece them all, you have cloud computing, you know, you have all these different satellites in, and you have this wonderful system that Nishan has created. I hope Nishan will maybe demo it when he talks. The easier web link for you to remember is satellitedams.net. So if you have internet in front of you, try to go check it out. I will click on it and see if I can take you there. If you bear with me a little bit. So I think it's taking it. It just reroutes to the right website. And what you see here basically is
Dr.
for
Faisal,
15.
I think you are sharing the PowerPoint, so you need
right.
to.
I'll just thanks for that. Just give me 1 second, and let me share that. Yeah, I'm glad that you told me that. Okay, you should be able to see it now. So if you go to that website, and you will see all these 1,598 reservoirs. You click on any one of them, and you see many things. You see the area elevation curve, you see the surface area, you see the storage change, outflow, inflow, and something that's very important is rule curve. Rule curve is like an average based on storage change, based on last 5 years pattern. When does it store at highest level? When does it draw down? When does it hedge water? All that. Okay, so I'll stop here, have fun with it, and let me come back to my main presentation again. Just bear with me, please. Yeah. So that's what we can do. That's one classic example of cloud computing, using lots and lots of satellite missions, running a model, processing 2 to 3 terabytes of data a day to really see how much water will we have, where, when, what are the dams doing to our river systems. All right, next is, so these are just the same things that I just showed you, the many different elements of a reservoir monitoring system that you can estimate or get a handle of using remote sensing. All right. I'm going to take you now to Southeast Asia, to the Mekong River, where it's an interesting river system because many things happening. Lots of dams are being built now. This is a transboundary river. They have same challenges as you have in other international rivers, but it's evolving and developing very fast. And I want to show you what we're able to do today. So one thing is we can actually, like I said, we can hack the operating pattern of reservoirs. Same concept as I alluded to before. You have satellites, like in this case, Landsat, that tells you what the surface area is, and you keep monitoring it for a long time, and then you already have area elevation curve, so you can get the storage change, and you can get an average pattern of when is the reservoir storing maximum amount of water, when is it storing the minimum amount of water. And typically in Southeast Asia, if it's a smaller and medium-sized dam, they tend to follow the monsoonal hydrology. There's a few months lag. So this concept, this schematic is shown here, just like I showed you before. And we have tested these rule curves. So here's like 2 reservoirs in Thailand. We just used purely satellite data. We tried to estimate the rule curve with some, this red line that you see, the dashed, or for Ubul Ratana Reservoir, or the solid red line here. And then we compared it with the published rule curve, which is the black and the gray line. They give you a range, of course, because rule curves tend to have sometimes like a rule curve for wet years, a rule curve for dry years. And you see that they fit exactly very well. And we derived these red line, the satellite estimated rule curve, using purely satellite data. We did not rely on any ground data from any country, any agency. So you're able to do that with a good amount of confidence now. All right, so this information that historically used to be secretive, not shared, is no longer secretive anymore. Anyone can really hack and estimate that. We can also do a couple of other things. We can estimate how long the water stays behind a reservoir. We call it residence time. If you just assume the reservoir to be a plug for reactor, whenever new water flows into the reservoir, you assume the oldest water in the front of the dam flows out. Then you can come up with some terms like, I will call it, flow alteration. It is outflow minus inflow over inflow. But you get an idea of how long the water stays behind the reservoir. So we were even able to, for every single dam, figure out what the delay is. It's kind of like looking at, say, when you're driving, say, in a big city and there's traffic jam. Yeah, you're at an intersection. Which intersection has the longest traffic jam, where you have to wait the longest before you can overcome the traffic and go and keep moving again? So it's letting you know that. So these circles that you see, the bigger the circle, it means the longer the residence time. So we have seen in the Mekong River is typically overall, with all the dams we have built so far, we have delayed the flow of water from the river basin to the ocean, South China Sea, by about 1 to 2 months. But there are many reservoirs individually that delay the water flow, or it keeps the water for anywhere from sometimes 1 to 4 months, especially these big ones in China. So it means the water will stay there for that long and then be released. And why is it important for us? Well, it's important for us for many things. You know, the longer the water stays, you have more sedimentation, you have more methane gas emission, you have other water quality challenges, you have ecosystem aquatic challenges, biodiversity. The reservoir will tend to stratify faster that way if it's not continuously mixed and all that. So it's a very key parameter, especially the ecosystem or resource managers needed, that we're now able to figure out using purely remote sensing. All right, then also how cold or warm the water is. Shahriar will talk more about this, I think, on Wednesday, if I'm not mistaken. But just very briefly, you know, a lot of these satellites that I just showed you earlier, they tend to have a channel or a sensor that can measure thermal infrared radiation, which is basically an indication of how warm or cold that surface is on the ground, the target. So using satellite data, we can estimate the surface river temperature or the surface water temperature. Here you see for one particular river system where there's a reservoir here. I don't remember exactly which one this is, but the surface reservoir temperature, the reservoir surface temperature upstream is a lot warmer. You can see it's red, and downstream it's cooler. Now, why is it cooler? If it's especially a hydropower dam, it's probably releasing water from the bottom of the reservoir, which tends to be cooler. And you can clearly see the difference in the temperature. It's almost 3 degrees different, the surface temperatures upstream and downstream of dam. And I think with Shahriar's talk, you'll know more about it. So we looked into the 3S rivers of the Mekong River system, where there were a lot of dams built since the 70s. And we have been able to actually tie the observed temperature changes downstream, especially the cooling of the rivers downstream, with the hydropower dams that were built. Using entirely remote sensing data, thermal infrared data from Landsat satellite mission. And we verified that or validated that with in situ measurements. This figure is particularly interesting. You can see here, here's the 3S river that joins the Mekong River. And this water here, the 3S, is cooler, and it's been going down. You know, since the 1990s, the temperature has been going down, the surface river temperature. And Mekong River has been a little warmer, but Mekong River temperature upstream versus downstream, there's a temperature difference. In fact, downstream is cooler because there is cool water coming from the 3S rivers. And you can detect that from the satellite remote sensing. And that cooling signature goes almost like up to 200 kilometers downstream. So you're able to do all this, and this river temperatures can be quite critical for fish migration and other, maybe water management or other kind of resource management needs. And this is a very recent finding or a topic that we're working on, even in scientific literature. So it's really bringing different communities together, because previously we had no idea that using satellite remote sensing, you could detect the thermal modifications to the river caused by reservoir operation. All right, so next is, like I mentioned, why do we expect a cooler temperatures? Because the reservoirs behind the dam stratify, and the bottom layer called the hypolimnion for a large part of the year tends to be cooler. And if you're doing hydropower, like you're doing in Aswan Dam, High Aswan Dam, you're basically pumping the cool water downstream. And by the way, for Hossain Dam, we've also seen a temperature change downstream versus the upstream reservoir surface temperature. All right, coming to the last topics of this, and then we'll end very quickly. Let's talk a little bit about food. And we're going to focus on South Asia here. So in South Asia, you know, we actually don't have a very water efficient system for growing food. If you look at these numbers here, China does a lot better. For every meter cube of water, it grows almost 1 kilogram of staple food. India and Pakistan, they're very wasteful, especially if you see in Pakistan, it's like for 1 meter cube of water, it's barely 0.13 kilogram of food. And if you look here on the right, it's a map based on another satellite data called GRACE. We won't cover it in this workshop, I think, but GRACE stands for Gravity, Recovery, and Climate Experiment. It can measure gravity. And measuring gravity, it tells us how much is the total storage change in that water system. Especially, it tells us if you're losing or gaining groundwater. And if you look at this map on your right, you will see that Western India and Pakistan, there's this big red circle. It's been losing water. It's been declining water since the 1990s or 2000, ever since GRACE started giving data since 2002. And there are some estimates by the Indian government that says that Western India may run out of water in 20 to 30 years by the Central Groundwater Board. And that region, by the way, is the breadbasket of the region. It feeds almost close to 300 to 400 million people. So one idea, we have to solve this issue because at the root of why this groundwater is declining and we have such low water efficiency is farmers use too much water. By the way, in my own literature surveys, or what I have learned is that in the Nile Valley, I think Nile Valley has very high crop productivity rates. I think for rice, it's got one of the highest tons of rice that it's able to grow per hectare. It's very fertile, and I think the water use is much more efficient than it is in South Asia. So I think in the Nile, things are a lot better when it comes to water use. But nevertheless, in South Asia, because farmers are using too much water, we came up with this system based on satellites. And of course, numerical weather prediction models, where we tell farmers when not to irrigate or when to irrigate based on what the crops need. So this is something you can do. Basically, you calculate your crop water demand. That's for today or the next week. You also calculate the rainfall you had today or past, or rainfall you expect to have in future. And then you fire these advisories, text messages to their phone, and they irrigate accordingly. So our group has been at the forefront of, thanks to all the hard work of Hisham, Shahryar, Nishan, and Indira, who are talking all in today's workshop. We now have a system that's running where farmers are getting these advisories using a lot of satellite remote sensing data. So it's addressing the food aspect of it and the water aspect, where a lot of the water is coming from reservoirs and rivers as well as the ground. Now, all this is nice. I've shared with you the potential of satellite remote sensing, but this discussion won't be complete, or this presentation won't be complete, if we don't talk about, very honestly, about the cons or the downsides of satellite remote sensing, which is absolutely critical for all of us to be aware of if you want to make the best use of satellite remote sensing data. See, if you're not careful, if you're not aware of the pros and cons, satellite remote sensing can be a double-edged sword. You may misuse, and it may end up actually doing worse than what you were doing without the use of the data. So the first thing to understand is there's a scale issue. Scale means, it's representative spatially or temporally over a certain domain. It's not a super precise over a small area like when you do a rain gauge. It's not giving you a rainfall information right at that point. In fact, if you're using microwave data for precipitation or discharge, they have a scale limitation of up to a few kilometers. That's the finest scale you can go down. So you have to keep that in mind. Or if you're using some other wavelength or other data, if you're doing vegetation, yes, there might be 30 meter or 60 meter resolution. So you have to always ask yourself, at what scale is it safe for me to use to make those decisions or to use that as a variable? Then you have uncertainty issues. Uncertainty issues, it's not just necessarily the errors. Of course, there are errors. Error means, how is it different from the truth if you know what the truth is? But uncertainty here means, if you're to repeat the same measurement, would you get the same value or not? If you're not getting it, if it's varying, if it's not precise, that's uncertainty. It's kind of like, say, I'm asking someone what the time is. Every time I ask that person what the time is, he or she gives me a different answer by a few seconds or minutes because, it's always, there's a bit of randomness to it. So you have to understand that there's uncertainty, and of course there is errors. And keep in mind, satellite remote sensing, as you figured out by now, based on the definition I shared with you, it's an indirect way of estimating your geophysical variables. It's not a direct method. So it's based on some statistical relationship, lots of assumptions and all that. So there will be uncertainty and there will be errors too. Then you have these loss of signal, attenuation. Sometimes you don't get any data at all. As an example, what I can tell you is the SWAT mission that I told you about that will fly in 2022, that will give us discharge. Unfortunately, we will not be able to have discharge information or say the storage information of lakes where it's raining very heavily, because when it's raining, the satellite will not work very effectively. So we have to know about these, and a lot of times the data will have these quality flags. And then finally, a lot of these data products that are out there from satellite missions, they're not like quote unquote fully industry standard, ready to use, quality controlled. They typically tend to change. They tend to evolve. The algorithms change from time to time. Lots of parameters change. The product names change. The format changes. So you have to sort of stay on top of it, and you have to understand how it's changing so that you're using it in the right way. So there are some challenges to that, and hopefully you will get an appreciation of that. So here's an example here. I have 3 different satellite rainfall products over the US. One is called 3B42RT. This is CMORPH. This is Persian. So later on, you may be able to figure out the satellite rainfall data products. And what you see is that the average rainfall over the US, each product is giving you a different answer. So there is uncertainty there, right in front of you. Qualitatively, the maps may look similar, but if you really zoom in, you will see that you have different numbers to it. And then each one of them have different scales. Persian is like a 4x4 kilometer data product. This one is, at least back then, it was 25 kilometers and all that. And then if you're not aware of the errors associated with it, and then you immediately plug it in a hydrologic model, you may get very bad or useless results. So here's an example here. This is the simulated stream flow using satellite rainfall data over this Ganges-Brahmaputra River basin at a location without any adjustments to the precipitation data. So the red line is the observed discharge, and the black line is your simulated discharge. So you see how overestimated it is. So there's a big bias issue. And there are ways to correct it. In this case, what Nishan has come up with is that he uses gauge information in real time and he adjusts the satellite rainfall data. Once you do that, you will see that the solid red line you see, which is simulated by satellite data, becomes much closer to the observed discharge data. And of course, your blue line is your without doing any adjustments. The point I'm making here is that you need to be very careful. You need to understand the scale issues, the error issues, the uncertainty issues, the signal loss issues and all that, and then make sure you're using it in the right way, whether it's for research, whether it's for decision-making, management, and all that. The last example, I believe this is for precipitation. Precipitation is always challenging when you're trying to do remote sensing off over land versus over ocean. But you and me, if you're sensing rivers, we're interested in precipitation remote sensing over land, right? Not over ocean. But over land, The challenge becomes particularly more when the land is cold. You know, the clouds tend to be cold, which is, if it's warmer than the land, it can do good remote sensing. But if you see on the right side, if it tends to be a little colder, if snow is falling, the clouds tend to be the similar temperature as the land, and the remote sensing is not able to figure out which parts are precipitating versus which parts are not. And I'll just put you the different types of clouds we have out there. You see on your right, you have thunderstorms, right? They rain heavily. And a lot of satellite remote sensing tends to work on the basis of what is the temperature of the cloud top. So this thunderstorm cloud that you see on the right, it will think, okay, it must be a thunderstorm because the cloud top is cold, and it will say it's raining heavily. However, a lot of these other clouds you see next to it, cirrus and cirrostratus, they never rain. They also look cold. So satellite really won't know that these are non-precipitating clouds, and they may mistakenly assign rainfall to these clouds. So these are some of the complexities that are out there that you have to be aware of. And the point I'm making is, I think the right use of remote sensing from satellite for water requires a good amount of humility and an open mind and some good checking of the pros and cons before you can embark on using it for whatever scientific investigation you're interested in or for your decision-making system. The human resources challenge, very quickly, this is exactly what Hisham is trying to achieve, I believe, in this workshop, is to get a lot of people, us, talking about it, learning from each other, and trying to keep up with the state of the art. That is always a challenge, and how to do it. One good thing is in our group, thanks to some excellent members like Hisham, Nishan, Shahryar, we've been able to do this for a long time. And that's what we do. So these are some pictures from past workshops I used to run, and now Hisham's taking over. Hisham's doing some excellent stuff today and this week. And we hope that by exchanging a lot of information and having two-way feedback, we'll learn a lot more. And hopefully we will do a lot more of these workshops so that it benefits the audience and benefits the stakeholders in trying to come up with the best use of remote sensing data. And this is very critical because at the end of the day, if you want to create systems that are used independently by the stakeholder, you need to have this training. So here's an example. We have a system for groundwater management in Pakistan government that took 1 year. But as that's a major improvement from our previous system we built for flood forecasting for Bangladesh government. It took us 5 years. And then we also improved on how we train human resources. Now we're able to even do it in 4 months, to come up with a system, train the staff, help them figure out what's best. So this brings me to the end of my talk. And I hope I've been able to set the stage and get you interested in wanting to know more in more detail about what sensing of rivers can be done or is afforded by satellite remote sensing. And just some key take-home messages are that I hope you can remember is, one is satellites are becoming increasingly common, more publicly available for monitoring our water resources because we're seeing more and more missions out there. And then there's massive amount of data that is publicly available. So we have to know what's the best way to use it. However, these satellite data require careful understanding of the pros and cons. And if we really want to create solutions, of course, we can't build solutions. We have to co-build solutions, meaning we have to build solutions hand in hand with the stakeholder agency, where the problem defines the solution. That's very critical. So training, workshops like what Hisham is doing today, and hopefully he will do more of these in coming years and months, is very critical. So building capacity is something that I stress is very important if we want to solve problems in the water sector, and kind of tying it back to what Hisham's vision is, have more peace, global peace. And seems like today we have International Peace Day. We really have to help each other improve our capacity, to handle data, understand what it means, and help each other create systems that have meaning to it. So just my acknowledgements, and I'll take some questions now. I just stopped sharing. So if you have any questions, be happy to take.
Thanks very
And
much.
yes,
Yeah, thanks very much. It's a very informative presentation. I really appreciate that, and I hope every one of the participants they learn about the not only the pros of the satellite remote sensing, but also the cons. So thanks very much. And let's take the first question. I think Muhammad Ahmed Hazak is raising his hand. Yeah, you can go ahead and unmute yourself and turn on your videos if you want and ask a question.
Or you can put it in the chat box too.
Yeah, I think he's raising his hand, so I think you can just unmute yourself, Muhammad.
Or he said he wanted the presentation. So the presentation will be available in the shared folder.
Okay. This is your question. Okay, no problem. So, yeah.
Any other questions? I'll be happy to take them. And you're welcome to ask me by email also, anytime.
So Awad Ali is raising his hand. Go ahead, Awad.
Okay, hello, how are you? I hope everything is going okay with you.
Yes.
Thank you, Professor Faisal, for your presentation. It was very informative. Thank you so much. So now I'm asking about the uncertainty of this remote sensing. Till what extent we could use it in our research, and when we need to calibrate it with observed data? This is my question.
Okay, so thank you for your nice comments, Awad. So the answer to your question depends on what you're trying to do. You know, you may be interested in hydrologic modeling, you may be especially interested in stream flow modeling, or you may be interested in water balance modeling or reservoir operations. So first ask yourself what you're trying to do, and then knowing that the satellite data or the set of data sets you're using will have uncertainty, try to test out what the uncertainty is if you have some reference data, maybe over a standard region. For example, Hisham's done a lot of work on the Nile River system, the High Aswan Dam, you know, the reservoirs and all that. He also had access to data, reference data, so he was in a position to compare. So my recommendation is maybe if you have such things where you have some reference data set, try to compare and see what is the uncertainty and what is the error, and then figure out, okay, if there's a bias is easy to adjust. All you do is you do a simple adjustment. What is that bias? If there's no bias, if there's something else, maybe you think about, maybe I should do more averaging, maybe I need to figure out the scale. So there's some investigation or some trial and error involved in that case to figure that out. I'll give you one example is when we first set up the hydrologic model for Brahmaputra and Ganges Basin, that was like 7-8 years ago using satellite data and a lot of satellite products. We weren't sure what grid cell scale we should be using it at. So we played with it, you know, we played with 50 kilometer by kilometer scales, 25 kilometer, 12.5 kilometer, to see what is scale where it responds best. And of course, there's a dependency on the model that you're using also. And then you try to figure out the best result, and then the scale, and then calibrate accordingly. So my answer is a little nebulous to you in the sense that it depends on what you're trying to do, and you have to sort of trial and error and figure it out yourself.
Okay. Thank you so much.
Thanks, Dr. Faisal. I think Alamin is raising his hand, so you can unmute yourself. Yeah, go ahead.
Yeah, okay. Hello, everyone. Thank you, Professor Faisal, for this presentation. I just wanted to ask a question concerning the measurement gauges. You said that they have declined, so I want to know the reason behind, what is the reason behind the remarkable decline in the measurement gauges? Have they been replaced or something, or by different facilities, or?
Yeah, thank you, great question. So when we say decline, there are two things to look into it. One is in the US, we have about, say for streamflow gauges, about 7,000 gauges or so. We haven't really expanded on it, and we've lost a lot of gauges that had 30 or more years of data because of money issues, you know, the economics. So that's even happening sometimes in the US. But US overall hasn't lost a lot of streamflow gauges. What you saw in the map was with GRDC. So GRDC is Global Runoff Data Center. It's based in Germany, where it collects all these gauge data based on agreements it has with different countries. And ever since, 2000 or so, it's been challenging to kind of collect almost in real time and make it available publicly for everyone, in the world. And a lot of it is, I believe, again, because of cost issues, economics, especially in the developing world. And a lot of it is maybe in lack of institutional frameworks and sharing. So it's a complex situation. I don't think countries overall, especially countries from developing countries, really have a very concerted plan, like a multinational plan to invest in a lot of in situ gauge networks, like they do with, say, sharing weather data. When it comes to weather data, WMO, World Meteorological Organization, has this great agreement with all these countries, and all the countries' individual weather stations, they report the weather data once or twice a day, which is then used to initialize the global weather models. We don't have anything like that yet for stream flow or soil moisture or, whatnot when it comes to water issues. So that's one of the bottlenecks. But to sum up the answer, I believe it's mostly the economics and the human resources challenges, why it's been sort of going down here when it comes to gauges.
Okay, thank you.
I think we're kind of running a little late, but let's take one more question. I think Muhammad is I'm not sure if this is he's raising your hand. It's not working well. Yeah, Muhammad, you can go ahead and ask the question if your headphone is not working. No, something. Yeah, go ahead, Muhammad, and ask your question. I think we can hear you now. No.
Or you can type it in the chat
Yeah,
box, or you can email me.
Because we
any
cannot.
of those.
Yeah, we cannot hear you, Muhammad. So you can type it, or you can just email Dr. Faisal anytime. I think we are. Any other questions? I mean, we can take one more question if you have. Yeah, if not, I think. Yeah, thanks very much, Dr. Faisal. Yeah, that's a very great session to get an idea about the remote sensing and the applications in water resources. So yeah, I think we will have a break for 15 minutes, but just as I said, before going to a break, let's just, if you can please turn on your camera and let's take a group photo for our workshop. So,
and I just quickly shared my email address for anyone else who wants to contact me later.
Yeah. And yeah, yeah, thanks everyone for turning on your camera. It's great to see some of the colleagues at Alexander University. Thanks for joining. Thanks everyone. Yeah. Yeah, I think we need to take a, yeah, because, yeah, I'll just take
need to take two.
Yeah, because it's not feeding, so let me take one more.
Everybody has to smile.
Yeah, please smile. Yeah, I think that's great. Thanks very much for joining, and let's take a break for maybe, I think we should take it for 8 minutes to start 9:30, but like let's plan to start at maybe 9:35. Yeah, let's start the next session 9:35. We have a presentation session by Nishan. He will talk about the big data and cloud computing. So yeah, take a break for maybe like 10 minutes and see you soon.